So my name is Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I lead programming language design and evolution. My job is to make every major language a GPU language, from Fortran to C++ to Python to Rust to JavaScript. So I'm involved in the leadership of many programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Languages Standards Committee. So today, we're going to explore the tools, libraries, and best practices that you should use to write idiomatic and modern CUDA C++ code. So who here has written code that runs on a GPU? Show of hands. Who here has used CUDA C++ specifically? Okay, cool. About 50-ish. That's like roughly what we're looking for. So first of all, for those of you who don't use CUDA C++, what is CUDA C++ and why would we want to use it? And also, like, what are GPUs? Why would we want to use GPUs? So modern CPUs and GPUs are both general purpose processors that can run almost any kind of code. They differ in what types of workloads they are optimized for. So CPUs are optimized for latency. They have more powerful cores and threads, but less of them. And they have less latency to access memory and typically more memory to access at the cost of much lower throughput. GPUs are optimized for bandwidth and parallelism. They can run hundreds of thousands of threads, and their memory latency is higher, but the memory throughput that they get is much greater. So how do we program a GPU in C++? Well, with CUDA C++ and NVIDIA's accelerated libraries. So what exactly is CUDA C++? CUDA C++ is an extension of standard C++ for writing programs that simultaneously run on CPUs, which we call hosts, and GPUs, which we call devices. So in host code, you can write regular C++, any standard C++ you can use. And in device code, most but not all of standard C++ is supported today. So for example, today you can't throw exceptions. There are some restrictions about how host code and device code can interact. For example, a variable on the stack in device code can't be accessed by host code. So you don't have to write your CUDA C++ program from scratch. There is a diverse collection of CUDA accelerated libraries that you can and should leverage. These libraries have been carefully designed and tuned by ninjas at NVIDIA to provide speed of light performance. And so before you write any CUDA C++ code, you should first check if there is a library that will work for your use case. And if there is, you should try it out and you should benchmark it. And if it delivers the performance that you need, you should just use the library and don't reinvent the wheel. With that said, now let's dive in with our first CUDA C++ program of the night. So imagine that we have a bunch of cups of hot water, or tea perhaps, at different temperatures that are recorded by a thermometer in each cup. And we want to simulate how these cups will cool down. So we'll do this by applying Newton's law of cooling for a number of time steps. In standard C++, we would represent our set of cups with a stood vector of floats. And next, we will define our per cup cooling operator with a C++ lambda, which is just a way of writing a C++ function object. And then for each time step, we apply the operator to all of the cups using one of the standard C++ algorithms, stood transform. Now, when we compile this standard C++ code, our compiler lowers each function and operation to the appropriate instruction set for whatever processor we're targeting. So like if we're targeting an NVIDIA ARM CPU, it's going to lower to this instruction. But when we're writing a CUDA C++ program, there are two different target processors, the host and the device, and each has its own different instruction set. And so the CUDA C++ compiler in VCC will compile CUDA C++ code for different targets. But how does NVCC know what targets a particular function should be compiled for? That is what execution space annotations are for. So if you don't provide an execution space annotation, then the function will only be compiled for host code, meaning the CPU. You can also explicitly request this with the host annotation. And if a function has only the device annotation, then it will be compiled only for device code, meaning the GPU. And you won't be able to call it from host code. But if a function has both the host and the device annotation, then it can be used on both the CPU and the GPU. And that's what we've used on our operator here. So now our operator can run on the GPU, but we still need to actually invoke it there. Execution of a CUDA program always begins on the host, and work must be explicitly launched on the device. The transitions between host and device are always going to be explicit. You have to call a function that launches work on the GPU. CUDA C++ will not magically decide to run things on the GPU for you. So functions that are invoked on the device will stay on the device. You can't launch host functions from the device. So going back to our example, the work that we want to launch on the device is our std transform here. So we can launch this on the device using thrust transform. It does the same thing as std transform, but in parallel and on the device. Now it takes one additional parameter, an execution policy, which describes the user's requirement for how the algorithm can be parallelized. So in this case, we're asking for the algorithm to be launched in parallel on a CUDA device. We also need to make sure that the data is accessible on the device, which we can do by switching from std vector to thrust universal vector. So thrust is the C++ parallel algorithms library. Its execution policy algorithms that we just saw were actually the inspiration for the standard C++ parallel algorithms that were adopted in 2017. So thrust has implementations of those standard parallel algorithms, and also a collection of extensions and additions to these standard algorithms. Thrust also has heterogeneous containers that behave like std vector, but store their contents in different kinds of memory that are accessible to different kinds of processors. Now, std vector's contents might only be accessible in host code, depending on the type of platform you're on. When you construct or assign to a std vector, that operation is done in serial, which can be pretty slow if you're working with a large amount of data. Like if you've got like a 4 GB std vector, that's going to take a while to create on the host in a single thread. Now, thrust's universal vector, its contents were always accessible on both host and device code. And operations on all thrust vectors, like construction and assignment, are going to be executed in parallel on the device. Thrust also has a collection of iterators that can be used in conjunction with the thrust algorithms to compose more complex computational patterns. If you're familiar with ranges, a lot of it's similar ideas here. So standard C++ and thrust algorithms will typically iterate over sequences of objects, like, for example, the elements of a container. However, in numerical and scientific computing, we often want to iterate through indices instead of objects because we're applying some sort of stencil. So we can do this with thrust counting iterators. So a counting iterator is constructed from an integer and represents the range of all integers from that integer onwards. So when dereferenced, it's going to just return that integer. And when incremented, it will increment the integer. So by passing a counting iterator to a thrust algorithm like for each n, we can then iterate over indices instead of objects. So thrust also has a constant iterator, which will repeat the given number forever. Now, iterators can help fuse together operations into beefier and more efficient work. So suppose that we want to transform some data with one function f, and then we want to reduce it with a reduction op g. So there's two problems with this approach as shown on the screen. By default, the thrust algorithms are fork join synchronous, so each invocation launches its work on the device and then blocks on the host until that work completes. So in our example, this leads to an unnecessary latency bubble, which can degrade performance. We wait on the host for the transform to finish before we can start on the reduce, even though there's nothing that we need to do on the host with the result of that transform. So additionally, we've had to allocate ON temporary storage for the transformation, which will waste precious device memory and cause expensive and unnecessary loads and stores from device to global memory. So one way to address this problem is to fuse operations together into a single parallel invocation, which we can do with a transform iterator. So a transform iterator takes some other underlying iterator and a function. And when you iterate a transform iterator, you get the result of applying the function to the values from that underlying iterator. And this is completely lazy. So the function is only evaluated as needed when the elements of the returned iterator are accessed. So for example, here, f is not going to be evaluated until the elements of x are accessed in the reduction. So sometimes we need to combine together multiple inputs into a single iterator to pass to an algorithm. And we can do this with the zip iterator, which takes any number of other iterators and then produces tuples that are a combination of the values from those underlying iterators at the corresponding position. So for example, here we make a zip iterator from x and y. And when you dereference this iterator the first time, you'll get a 2-element tuple, x0 and y0. And then if we increment it and dereference it again, we'll get x1 and y1. So we can also use zip iterators to invoke algorithms on overlapping windows or stencils of elements. So for example, here, we're constructing a zip iterator to the adjacent pairs of elements of x, and then applying the function f to each pair with for each n. So f will be invoked with x0 and then x1, and then it will be invoked with x1 and x2, et cetera, until the end of the range. So let's look at another example that sort of combines all of these iterator ideas together. So suppose that we have two vectors of the same length, a and b, and we want to calculate the maximum difference between corresponding elements of each vector. So we can do this by first calculating the difference between each two elements, and then doing a max reduction of those differences. So we start off with two universal vectors, a and b, and then we calculate the differences between each two elements of a and b, storing it in a temporary vector that we've allocated. And then finally, we do a reduction of the differences with maximum as the reduction operator. Now we can improve this by replacing the transform with a zip iterator and a transform iterator. The zip iterator produces 2-element tuples of each corresponding element of a and b. And then the transform iterator takes that zip iterator and applies a lambda function to it that unpacks the tuple and computes the difference between the two values. Now, this pattern of transforming and then reducing is quite common and very powerful. So Thrust has a single algorithm called transform reduce that does this fusion with the transform iterator for you. It's equivalent to the code on the slide before. That's actually how it is implemented. And so this is known as map reduce in some domains. Now, we've used two new facilities in this example that I haven't explained yet. The first is a CUDA stood tuple instead of stood tuple, and then CUDA maximum, which is a function object, instead of stood max, which is just a function. So these are facilities from libcu++, which is CUDA C++'s foundational and standard library. So CUDA C++ will use your host platform's C++ compiler and C++ standard library for compiling host code. So it's going to use GCC, Clang, MSVC under the hood. And therefore, the facilities that are in the stood namespace come from the host C++ standard library, which are not designed to work on a GPU. And so those are all host only. Now, libcu++ provides a subset of the C++ standard library in the CUDA stood namespace, and all the facilities there can be used in and across host and device code. libcu++ also has many extensions to the C++ standard library, as well as modern C++ APIs for the CUDA runtime and device-side facilities. And you can find these in the CUDA : namespace. And then beta features that are not yet stable are in the CUDA experimental or CUDA X namespace. So now let's take a look at one of the most popular kinds of extended algorithms in Thrust, which is by-key algorithms. So by-key algorithms will divide the input up into contiguous groups and then invoke an underlying algorithm on each group. So you can think of them as like batched or segmented algorithms. So for example, suppose that we have some matrix and we want to take the sum of each row. So to use a by-key algorithm to solve this problem, we must first create a range of keys that define the groups that we want to reduce. So that's going to be a range of keys that defines the rows. So each set of consecutive keys that can pair equal will define a group. So in our example, all the elements in the same row should have the same key, and the value of that key can just be its row index. And we don't have to materialize these keys in memory. We can generate them with Thrust lazy iterators. So we use a counting iterator to generate the linearized location of each element. And then we determine its row by dividing by the number of columns using a transform iterator. So next, we'll need some storage for the sums for each row. And then we'll invoke our by-key algorithm. And in this case, we'll use reduce by key. The first parameter it takes is the input for the keys, which will just be the Thrust lazy iterators that we generated before. And then we'll have our values input, which is just our matrix M. And the underlying algorithm reduce is going to be applied to the values in each group. Next, we have our keys output. So by-key algorithms will copy one key for each group, which is just going to be the first one in the consecutive sequence, to the key output range. But in our case, we don't actually need the output keys. They'll just be the same as the index of each sum in the sums vector. And we don't want to do extra writes that are unnecessary because that's going to waste bandwidth. So we can use Thrust discard iterator here to ignore the outputs. So when you dereference a discard iterator, it just returns a special object that does nothing when you assign to it. Yeah. So finally, we have the values output, which will just be our sums vector. And that's it. We're done with this particular example. So there are a bunch of different by-key algorithms in Thrust, including reductions, scans, sorts, unique, merge, and then the set operations. And these are particularly useful for batching up operations that you need to perform on different groups of data. And doing that will enable more efficient parallel processing because you'll have a larger input set instead of calling the underlying algorithm n times. Now let's move on to another example, working with multidimensional data. Let's simulate my oven, which has a heating element on the top and on the bottom. That's a picture of me from during the pandemic with an apron that one of my interns got me that says I usually cook C++ standard, but today I'm making cakes. So we're going to simulate my oven on a 2D grid by solving the heat equation numerically with a 5-point stencil. So our solver function will take a Thrust execution policy, the dimensions of the grid, and two universal vectors, U, which represents the current state, and V, where the next state will be written. So we'll use a Thrust for each n over a counting iterator to implement our stencil. The for each n lambda will need to capture the grid. However, we can't just capture the universal vectors because if we capture them by value, then we'd be making a copy and that's not what we want. And we can't capture them by reference because while the contents of the vector can be accessed from the device, the vector object itself may not be in memory that the device can access. So instead, we obtain pointers to the vectors and we capture those instead. The first thing we do in the body of the lambda is reconstruct the multidimensional indices from the linear index. Next, we need to check if we're in the interior of the grid, in which case we need to apply the stencil. So here's what the stencil computation itself looks like. It's, a little hairy and complicated, but It's correctish. If we're on the boundary, then we don't have to change anything. Now, there's a couple different unfortunate things about this code. First of all, we have to do the thing where we capture the pointers. That's a little bit annoying. And then we have this repetitive and error-prone multidimensional indexing in the stencil operator itself. So what we really need here is a proper abstraction for multidimensional data. And it only took me 10 years, but I did get one into the C++ standard library, and that's what MDSpan is. It's a non-owning handle to multidimensional data. So it's basically a pointer plus metadata. So if you're familiar with std string view or std span, it's very similar to that, just for multidimensional data. So the layout of an MDSpan is configurable, and the dimensions can be specified either at runtime or at compile time. So copying them is cheap and trivial because you just copy the pointer, not the contents. And this means that you can capture them by value in a lambda that's going over to the device. So MDSpan has a powerful slicing facility called sub-MDSpan that produces new MDSpans that view a subset of the underlying data. So let's rewrite our heat equation solver to use MDSpans. So instead of taking universal vectors and then having to obtain pointers to them that we can capture, we can just take MDSpans, which can then be captured by value and copied to the device. So we replace that manual indexing with calls to MDSpan's index operator with the multidimensional coordinates. So now let's write a function to set up the initial state of the oven. So it's going to take a policy and an MDSpan to initialize. So we can break the grid down into 3 different regions that we need to set. We'll use sub-MDSpan, that MDSpan slicing operation, to obtain MDSpans to these 3 regions. So sub-MDSpan takes an MDSpan and 1 slice specifier for each dimension, which indicates which indices from that dimension should be selected. So a slice specifier could be a single index, it could be a range of indices, optionally with a stride, or it could be the entire dimension, which is indicated by full extent. So the first 2 regions that we need are the row at the top of the grid and the row at the bottom of the grid. And then the last region is the interior points, which is going to be everything except for the first and last row. And so then we'll set the top and bottom row to a high temperature, and we'll set the interior region to a lower temperature. So now let's write the time-stepping loop that's going to repeatedly call that solver function that we wrote a few minutes ago. So we're going to output the state of the system periodically during the loop. So after every compute steps evaluations, we'll do 1 output. And in total, we're going to do write steps times compute steps iterations. So we'll start by setting up our 2 universal vectors and constructing MDSpans to them. There's a thing coming down the road called MDArray, which is a owning container that avoids needing to set up the MDSpans separately. But for now, this is what you'd do. And then we'll initialize U with the function that we just wrote. And then next, every write step, we will save the current state by calling some save to file function on U. And then for every compute step, we'll call our solver function with U as the input and V as the output. And then we'll set the new state from the solve as the input for the next solve by swapping U and V. So as we discussed earlier, thrust algorithms are fork join synchronous by default. So they launch the device work, and then they wait until that work has completed before they return to the caller. So this introduces unnecessary waiting on the host and underutilization on the device because we can't launch the next piece of work until the first one finishes. So we want to be able to overlap the latency of launching device work, which is relatively high, so that our GPU will always have work in the queue and reach maximum utilization. That means we need asynchrony, and for that, we'll have to change the execution policy that we're using here. So the thrust CUDA par no sync policy will cause algorithms to not wait for the device work it launches. So the algorithm invocations will return immediately, and the caller will be responsible for synchronizing later. So in our case, we'll need to wait on all device work every write step before we call save to file. to ensure that the last compute step has completed before we begin writing. So this is a good start to making our code asynchronous, but the next step is to use CUDA streams. So a stream is a chain of device work that is executed in order. You can think of it like a queue. You can have thrust launch work on a specific stream by passing the stream to the on method of the execution policy. So here we asynchronously launch a for each applying F and a for each applying G on the device. And the F for each will complete execution before the G for each starts. A stream can record an event that host code can synchronize with, waiting for all work up until that event to complete. And you can do this in code by simply calling wait on the stream object, which will implicitly record the event and then block upon it. So in this case, it's going to wait for both of those for eaches to complete. Now, if we instead wait before the call to the G for each, then we'll only wait for the F for each. Now, we can create multiple streams that run concurrently on a single device, just as you can run multiple threads concurrently on a single host. And streams can wait upon other streams through events. So you can also explicitly record an event on one stream with the record event method. And then you can have another stream wait for that event by calling the overload of wait on a stream that does not take an event. Now, note that the host will not block on the event when you call this form of wait. It will just tell the stream to block on the event. And I recognize it's confusing to have both of those things on one function called wait, and I've told them to rename one of those two. So you can use streams to control where specific device, or on what specific device your code runs on. So by default, they're constructed on the first device, but you can explicitly construct them on any device on your system. And you can establish dependencies between streams running on different devices using events, just as we've discussed. So let's revisit our heat equation example and add streams. So we're going to create a stream, and then we're going to define an asynchronous policy that will run on that stream, and then we'll use that policy in all of our calls to thrust. So instead of waiting for all work on the device at the start of each write step, we'll just wait for the work that's on our particular stream. Now, there are some limits to thrust's support for asynchrony today, although those will largely be resolved in the near future. So today, it works great for algorithms like for each and transform. Some thrust algorithms either return a result that depends on the computation, or they allocate temporary storage for the computation. So today, these interfaces would block even with the par no sync policy. So for example, consider inclusive scan. So it returns an iterator to the end of the output, and that doesn't depend on the computation. So we can just compute it beforehand by incrementing the output iterator by the size of the input. Thrust assumes that everything's a random access iterator, so that's fine. However, unlike for each and transform, scan algorithms require temporary storage. And thrust has to allocate and deallocate this storage before the algorithm returns, which will block today, even with the par no sync policy. However, we do have an async allocation API in CUDA, and I've sent a PR to fix this that should hopefully be merged soon. So algorithms like copyIf return an iterator to the end of the output, but that depends on how many elements pass the predicate, which we won't know until the computation is complete. So these kinds of algorithms are implemented in terms of a scan. So they also need temporary storage. So thrust has to block before returning from these algorithms, even with the par no sync policy. And then reduction-based algorithms like reduce, count, find if, and max element return the result of the reduction, which requires blocking. So they also need to allocate temporary storage. So if we need asynchronous versions of these algorithms today, there's another lower level CUDA C++ algorithms library that we can use that is designed to be asynchronous from the ground up. In terms of thrust, what we'll do here is we're going to have to just add new variants to these algorithms, like a reduce into that takes an output iterator where it will write the reduction result to that location. There's no way to fix the current overloads. It's just inherent in the design that they're going to block. So that other library is called cub, and it is the CUDA C++ algorithm authoring toolkit. So cub provides cooperative building blocks for writing your own device-side parallel algorithms, so for writing your own CUDA C++ kernels. That's not the focus of our talk today, but if you're interested in that, there was a really great talk at NVIDIA's GTC conference this year about writing CUDA C++ kernels. There's a link here and a link at the end of the talk. Don't worry about taking a picture now. There will be a QR code at the end. So CUB also exposes device-wide algorithms that you launch from the host, just like Thrust, and that's the part of CUB that we're going to talk about today. So as I said, CUB is a little bit lower level than Thrust. So we just discussed how some Thrust algorithms need to allocate temporary storage, for example, reductions. So we implement GPU reductions today with two passes. The first pass divides the input up into chunks, each of which is handled by a block of threads, which will collectively reduce the entire chunk to a single value that is stored in a temporary array. And then the second pass will use a single block of threads to reduce the aggregate in the aggregates in the temporary array to a single result. And this approach means we don't have to do any grid-wide synchronizations. So with Thrust, the temporary array allocation and deallocation is done implicitly within the algorithm. Now with CUB, it's asynchronous by design, so it doesn't return the reduction result by value. Instead, it takes an iterator and then assigns the reduction result to that iterator. So when we call a CUB reduction, we need some device accessible storage for the result, which we've allocated right here. With CUB today, we must allocate the temporary storage explicitly. But first, we have to determine how much temporary storage we're going to actually need. And this is not trivial to figure out because it will depend on the algorithm that we're using, the data types being used, the operators being used, the specific device architecture. There's a whole big dispatch and tuning table. And so since you need the same information that you'd invoke the algorithm with to compute the temporary storage size, someone a long time ago thought it was a great idea to use the same interface to do both things, which is a little bit unfortunate. So the first two parameters to a CUB algorithm are a pointer to temporary storage and a reference to the temporary storage side. So if the pointer to temporary storage is null, then the algorithm will not be invoked, but instead the temporary storage size will be computed and assigned to the integral reference that you've passed in. And so then next we need to allocate the temporary storage, which we can do with a vector of CUDA std bytes. And then finally, we call the algorithm again, this time passing in a pointer to the temporary storage. And this time, the work will be asynchronously launched on the device. So let's rewrite our heat equation solver from before to use CUB. So CUB has a for each algorithm, just like Thrust. And this one's a little special because since it never needs temporary storage, you don't need to pass in a temporary storage pointer or a size. So CUB algorithms do not take execution policies, so we don't need to pass that in anymore. But we can specify what stream a CUB algorithm should run on. That's always going to be the last argument to a CUB algorithm. So we'll pass that in instead to our heat equation function. We're going to pass that in through a stream ref, which is a non-owning handle to a stream object. Now, we're still using a counting iterator here. Thrust iterators work great with CUB, and it's pretty common for people to use them together. But CUB has a better algorithm for this particular use case of iterating an MD span. So MD spans don't have iterators because multidimensional iterators would be inefficient on certain platforms. Like on CPUs, there's no way to implement a multidimensional iterator that's going to give you good code gen that won't inhibit vectorization. So the standards committee just decided not to have them. So CUB has this for each and extents algorithm, which we're also planning on adding to Thrust. And this just takes an MD span extents object instead of an iterator. And the MD span extents object describes the shape of the MD span. And so this function will just say what's the shape? And then I'll just invoke the operator that you've provided it with those multidimensional indices. So you don't have to reconstruct the multidimensional indexing here ourselves. And this is going to reduce complexity, and it can also increase performance because CUB will do the reconstruction for you in the fastest way possible. If reconstruction is needed at all, it could also choose to implement it with a natively multidimensional CUDA grid under the hood. So throughout this talk, we've been using Thrust universal vectors for device-accessible storage. Now, universal vectors are implemented with a feature called CUDA unified memory. So let's go under the hood and see how this actually works. So a universal vector is accessible from both host and device code. But in some cases, on some platforms, host and device code will have different physical memory. It's actually the common case for most of the platforms that y'all would be using. So where do the contents actually reside? In the host memory or in the device memory? So thrust universals vectors contents will start out on the device because that's where they are initialized. Universal memory has a first touch policy. So if we then access an element of the vector from the host, the CUDA platform may have to migrate the data from the device to the host. And the mechanisms for this transfer vary between platforms. Sometimes it is supported by hardware. Sometimes it goes through the operating system's page table. Sometimes it goes through a software layer. And on systems that have both an NVIDIA CPU and GPU, there may not actually be a migration at all, or the migration may be completely handled by hardware. The migrations won't move the entire vector. They'll just move a part of it. It won't be at the granularity of a single element. It'll be at the granularity of like a chunk. So if there is a migration, then we end up with 2 copies of that element and any other elements that were speculatively migrated. So there's going to be a good copy in host memory, and then there's a stale copy in device memory. Now, then if we access a different part of the vector later, then it will trigger another migration. And if we later access the first element from device code, then we have to migrate the element back. So with CUDA unified memory, the transfers are implicit and piecemeal. So this has advantages. It's a lot simpler to program, why we started with it, and it allows you to oversubscribe GPU memory because you can create a universal vector that has as much memory as your CPU has, and then the GPU will just page in or page out whichever parts it's accessing. But if we're not accessing the entire contents, it may be more efficient to do it this way if we're sparsely accessing the data set. However, if we're iterating through the entire vector, then it's going to be less performant to migrate the vector piece by piece instead of doing it all at once explicitly. So unified memory is just one of the options that we have available to us. It's the most user-friendly, which is why we've started with it. But we can also allocate memory that is tied to a particular host. Host vector will allocate memory that can only be accessed in host code, so it's like std vector. And then device vector will allocate memory that can only be accessed to in device code. And we actually have used this already because we used this to allocate the temporary storage for the cub reduce earlier because we never need to touch that in host code. And to transfer memory between memory spaces, we can use thrust copy, which works just like std copy, but unlike std copy, thrust copy understands the different memory spaces and the various ways of moving data between them, such as hardware DMA engines, various software mechanisms, optimized kernels, et cetera. And it's going to dispatch to the correct and most optimal mechanism when possible. So you should almost always be using this. So if we take a look again at our heat equation code, our save to file function will access the entire U vector on the host right here. And that will be an implicit device to host transfer, which is pretty expensive. So instead, if we can create a staging buffer in host-only memory, and then we explicitly copy from our problem state in device memory to the host memory staging buffer with thrust copy. So now, not only is our memory transfer more efficient, but we are also overlapping the compute with the I/O. So our code will first initialize the problem state asynchronously on the device, and then next we'll enter that outer write loop on the host. And then every write step, we start by copying U to buff. And then we immediately wait on the stream, ensuring that any previous compute and copy have completed before we continue. And then next, we asynchronously launch our heat equation solver compute steps times on our stream. And then on the host, we start outputting the staging buffer at the same time as those heat equation solves are happening on the GPU. And then we repeat this for every iteration of the outer write loop. And there's a couple more steps to optimizing this to make this overlap even better and the memory transfer even more efficient. But if you want to learn more about that, we've got a great tutorial to CUDA C++ available on our Accelerated Computing Hub. There will be a link on the last page of the slides where you can see the next few steps of optimizing. So we've only talked about a few of the many CUDA accelerated libraries today. They're sort of the core ones, but there's many more to explore, including math, machine learning, data science, simulation, physics, I/O, networking, and device-side programming. And if you want to learn more about what's available, we have a whole track of CUDA developer content that we launched this year at GTC, which is NVIDIA's developer conference. As I mentioned earlier, there's a talk that builds on this one by diving into the more advanced topic of writing your own CUDA kernels in C++. And there's also an equivalent to this talk in Python and an equivalent to the kernel authoring one in Python. We've also launched this whole new CUDA curriculum with tutorials and notebooks and other learning materials, which you can find on our Accelerated Computing Hub on GitHub, which are all open source. And I should acknowledge all of my colleagues who are behind all the technologies that we've covered here today. When I started working at NVIDIA back in 2017 and founded the CUDA C++ core libraries team, I was one of the only a few people in CUDA working on modern CUDA, on modern C++. And now we have a whole team working on the CUDA C++ developer toolbox led by Jake Hemstad and Georgy Evdoshenko. So they're doing great work, and they should be acknowledged for that. I think we got one more slide there. And I think that's it for this talk. I think we've got time to do the other talk. So you can ask me questions at the bar later. I'm feeling confident about the timing. We'll maybe take one question right now. Yeah.
Hey, in November last year, here we had Rainer Grimm talk about C++26. The thing he was most enthusiastic about, incredibly enthusiastic about, was studexec, which is an NVIDIA library. What's the relationship between that and what you've presented?
studexec is like the future. We're here today, and what we're doing with our new content is really to refresh how we teach the things that are out in the wild today. So CUDA is about 20 years old. A lot of the educational material is pretty out of date. We can't afford to wait until the new thing comes to teach people. And also, this is the technology that people have available to us today, which is why we talk not only about the cool things that you can do, but I highlighted the places where there are limitations, like Hub's weird, two-step call procedure to actually invoke an algorithm, or thrusts, the issues with the par no sync policy. So this is really focused on things that are out there in production today. studexec we have an implementation. It's been around for about 2 years, but not only is it still experimental, the standard hasn't shipped with it yet. So the design may change between now and the end. There may be some tweaks to senders before it ships. So it's like too early for us to give this sort of content for it.